start by the first problem because it is the longest one. Okay, and we will start another time. So I will start first with the following. Shows that true strain can be related to engineering strain through true strain equal ln of 1 plus engineering strain. So whenever I want to demonstrate a certain formula, I should go back to the initial definition. So first, what is the true strain? It's ln of L over L0. Okay, so I should try to find a relation between L over L0 and the engineering strain. To do this, I go back to the definition of engineering strain, which is E equals to L minus L0 over L0. I can write it in another form. It is L over L0 minus 1. Okay, so by taking this will appear this term for me, L over L0. Then if I take 1 to the other side, I get that 1 plus engineering strain equals to L over L0. And then if I replace back into my formula here, I can get the result desired, which is epsilon true equal to ln times 1 plus engineering epsilon. Okay, so this is how we can demonstrate this formula. So this is a simple problem. Let us go to another one. I have a tensile specimen is elongated to twice its original length. Determine the engineering strain and true strain for this task. If the metal has been strained in compression, determine the final compressed length of the specimen such that, first, the engineering strain is equal to the same value as in tension, but of course it will be negative value because of compression. And B, if the true strain would be equal to the same value as in tension. Again, it will be negative value because of compression. So the purpose of this example is that we will see that in part A the result is impossible, and this will show us that the true strain is a better measure of strain during plastic deformation. So let us do the problem. First, what they said that we have a specimen that is elongated to a final length of 2 times L0. Okay, so since we know this property, we are able to calculate the engineering strain, because the engineering strain by definition is the final length, which is 2L0, minus the initial length, which is L0, over L0. So you can see here that L0 will be simplified. So we get 1 over 1, which is 1. Okay, now concerning the true strain, the definition of epsilon true is equal to L final, which is 2L0, over the initial length, which is L0. So 2 over L0 will be also simplified. So it is equal to, it is ln of this number. So it's ln of 2. Okay. Now, the question is, they want us to determine what should be what is the final height in compression if I want to obtain the same engineering strain first, and if I want to obtain the same the same true strain. First, if I want to have the same engineering strain in compression, this means that, of course, in absolute value, this means that engineering strain is -1. Now, if I apply this formula, I have that in compression, what is the engineering strain? It is the final height minus the initial height over the initial height. This should be equal to -1. As you can see here, to have this equal to -1, h should be 0. The value of h should be 0. But in real case, okay, this is impossible. I cannot reduce to a 0 height. So this will tell you that this value of engineering strain for compression is not physical. Okay. Now, if I want to compare what should be the final height to obtain similar true strain, okay, I will apply that to have same true strain. I should have that the definition of true strain is true strain equal to ln of h over h0, and it is equal here to minus, I will take the same value but put a minus because it's a compression test. So mine is 0.693. And in this way, I can calculate what will be the corresponding relation between H and H0. Okay, so here this will tell me that true strain is a better measure of strain for plastic deformation. Okay, now another problem on Brinell hardness. In a Brinell hardness test, a 1,500 kilogram load is pressed into a specimen using a 10 millimeter diameter hardened steel bore. The resulting indentation has a diameter of 3.2 millimeter. First, determine the Brinell hardness number for the metal, and second, if the specimen is steel, estimate the tensile strength of the steel. So all we have to do here is a numerical application, and we just should pay attention for units. Okay, so here they gave us the Brinell hardness. This is the Brinell hardness formula. You have it in your formula sheet. You should pay attention that in this formula, F is in kilogram. So it corresponds to the force, okay, over G, because the weight is a force, okay, and we can express the force in kilogram by just considering the weight as defined as M times G. So if I give you the mass, it is equivalent to giving you the weight. This is why sometimes they put the unit of force in kilogram, and they represent what should be the mass to give the equivalent force in Newton. Okay, so if I give you the force in Newton, you should pay attention to not replace it in Newton. You should divide by G in order to transform into kilogram. Okay, so F should be in kilogram, and dB and di should be in millimeter. So if I give you in centimeter or in any other unit, you should convert to millimeter. Okay, now once you replace numerically the force and diameters by their values here, you will get the value of the Brinell hardness. Okay, it is BHN, Brinell hardness. Okay, so this is it has its own scale. It's 182 Brinell hardness, BHN, and we know that from the course material that we have a property, an empirical relation that will allow us to determine the tensile strength of steel from the Brinell hardness. The relation is we should multiply the Brinell hardness simply by 3.45. And when we do this, we get the value of the tensile strength will be in megapascal. Okay. Any question on these problems? So we'll continue to solve these problems next time.
Thank you, doctor.
Please, especially the first problem, you need to draw a figure. I want you to try to do it on your own, okay? And we will correct it together on Monday. Okay, bye.
Okay,
Thank you,
doctor.
Doctor. Have a nice weekend.
Welcome you too.